Okay, today is November 7th, 2011. This is lesson 4.1 and 2 put together. Our objectives are to learn about the characteristics of quadratic expressions. We're going to go into quadratic equations of quadratic expressions, which this is our standard form, y equals ax squared plus bx plus c. We're going to talk about parabolas, vertex, axis of symmetry, finite differences. We're going to have to make that font a little smaller. Oh, no, we won't. First and second differences. Okay. Now, the first thing we're going to talk about is lines of best fit. Now, we're used to seeing, do it in blue. Let's say we had some relationship. We're looking at a scatter plot graph. And all the data's put like this. If I was to put a line of best fit, we would have a straight line roughly going through the middle. This would be a good line of best fit. Okay? Let's say now I have data that looks something like this. There we go. A line won't be sufficient. This doesn't really give us a good indication of the data after a certain point, and either does this. So a line isn't sufficient. What we'll be looking for is a curve of best fit, which could be something like this. Okay? That's okay. That's roughly what we're looking for, something like this, okay? So this would be known as a curve of best fit. Okay? I know it's not perfect. Now, this is what's important. What kind of relationship does a line of best fit represent? There's a name for it, starts with an L. Yes. This is a linear relationship. Okay? Now, what we're about to learn is a curve of best fit, or something like that. This type of relationship is called quadratic. Okay? So this relationship here is considered a quadratic. That's nice, man. Quadratic relationship, okay? Now, with a quadratic relationship, that's a little better. With a quadratic relationship, it's a curve, okay? And another word for a curve is a parabola. So the shape that it creates, which is this type of curve, is known as a parabola. I need you guys to know this, okay? That's why it's one of our key words over there. Parabola is one of the key words we're learning. Okay? Along with that, there are parts of a parabola. Just like in a linear relationship, when it crosses here, this is called a y-intercept. Okay? If it were to cross over here on our x-axis, we know we have x-intercepts. They're both the same. We can have y and x-intercepts for parabolas. Okay? We also have a slope on a linear relationship. We have slope with linear. Let's try to separate these two. Okay, up there. So we have slope with linear. With a parabola, we have a couple other things. First of all, what we have, one part of it is considered the vertex, okay? And the vertex will be the lowest point of a parabola. It could also be the highest point depending on which way the parabola is facing, okay? So this parabola is opening upwards. If you see the U shape there, it's considered opening upwards, Okay, so what I'm going to do is I'm going to quickly create another small graph. Okay, the lowest point here, this is the vertex. It's also known as the minimum. Okay, because it has the lowest point, that's the minimum value of the vertex. It has a point that's lowest, and then it starts to go up again. That's assuming, just like in English, we're reading left to right. This thing would go down, hit the minimum, and then start to go up again when we're going in this direction. Okay? Just like our second example, here's our first example. Our second example, this is still our vertex. But in this case, it's considered a maximum. Okay? This is the maximum point of the vertex. Now, with that, the vertex is also at a point called the axis of symmetry. The axis of symmetry is a line that goes directly through the middle of the parabola. So it goes through the vertex. And what it is if I were to flip this from left to right along this axis of symmetry, it would still be the exact same shape. Okay? Every parabola will have an axis of symmetry, which goes directly through the middle of the shape. Okay? So this is called the axis of symmetry. Sometimes I call it AOS, axis of symmetry, okay? Let's fix that. Okay, so just to reiterate quickly, here's our vertex.
Excuse me, sorry for the interruption.
It's also, because this is a parabola, now we normally put arrows on the end because it will go on forever. The lines aren't parallel. They'll constantly get wider and wider. It's just a very, very steep slope. And the slope is consistently changing also. So the vertex passes through our axis of symmetry, we know. So we're going to put that as AOS. It's also, in this case, a minimum value. Okay? In this case, it's our vertex again, the highest or lowest point. In this case, it's the highest, also known as the maximum. And it also passes through our axis of symmetry. Both of these shapes, both of these shapes are parabolas. Now, the equation that represents these shapes we've looked at when we were doing factoring and expanding. If you guys recall, I'd given you guys this equation. Y is equal to squared plus x plus c. This was our A value, our B value, and our C value. This is the equation of a quadratic. Okay? So, the equation of a quadratic is written like this. I want you guys to recognize that if you were to graph this equation, it will be in this shape of a parabola. Okay, so this is example 1 in your textbook. Okay? They've given us some data, x and the y values, and we've plotted the points. If we look at this, a line of best fit doesn't quite represent how these points are moving. Okay? So we're probably going to end up with a curve of best fit, and it looks like this curve is what type of shape? Yes. So this is a parabola. Okay? This shape is a parabola. It's a curved line of best fit. It's also opening downwards. Okay? So I can tell by looking at this that this is what type of relationship. Starts with a Q. There we go. This is a quadratic relationship. Just by looking at that. Okay? But I did have to plot all the points. There is another way. There is another way to find out if it's a quadratic relationship or a linear relationship without plotting them. Okay? So what I'm going to be doing is I'm going to find the differences. So I'm going to be subtracting the differences between the y values. Okay? So we're going to set up each pair and subtract one from the other. So our first set, I'm doing 6.2, subtract 17.2. I get negative 11. Our next set, I'm going to take 17.2 and subtract 23.8, negative 6.6. Okay. Now, if you want you guys to notice, I took the top number, subtracted the next one. Then I took the top number again, subtracted the next one. Keep that same pattern. Don't jump from the bottom one to the top to the bottom, because you're going to mix up your positive and negative signs. In my next one, I'm going to take 23.8, subtract 26, 2.2. Then I take 26, subtract 23.8, 2.2 again. 23, subtract 17.2, I'm going to get 6.6. And finally, I'm going to get 11 again. These are called first differences. Okay? These were my first differences. Are they the same? Are they the same? No. All of these are different numbers.
They are so equal. In every way.
So, all of them are different numbers. Okay? That means, and I should have said this before. First differences. If the numbers are all the exact same, that means we have a linear relationship. Okay? If they're the same, it would be linear. So are they linear? No. We can tell that by looking at our graph. We clearly know this isn't a linear relationship. The next thing I'm going to do is subtract those terms.
Too much math.
That will give me my second differences. So I take negative 11 and I subtract negative 6.6. I get negative 4.4. Then I take negative 6.6. Negative 6.6, subtract negative 2.2. I get negative 4.4. Then I take 2.2. Sorry, I didn't draw those lines. Let's fix those a little. Then I take 2.2, or sorry, I take negative 2.2 and subtract 2.2. I get negative 4.2 again. What did I say? Sorry, 4.4. I take 2.2, subtract 6.6, and I get negative 4.2. Oh, I keep saying that wrong. 4.4. And finally, 6.6, subtract 11, negative 4.4. Now, here's a question. Are all of these differences the same? Yes. These represent quadratic relationships. So, if they're all the same, that tells us that it is a quadratic relationship. So, let's recap. First differences. If all of the first differences are the same, that means we have a linear relationship. If they're not, we take it a step further. We take the second differences, so the differences of the first differences. If they're the same, they're quadratic. If they're not, then they're neither. If neither first or second differences are the same, then we don't have a quadratic or a linear relationship. Now, from plotting the points, we easily could tell it's quadratic, but we may have so many points it takes a very long time to plot it. So taking first and second differences is a way to solve if something is linear or quadratic in terms of its relationship. Finally, this is our quadratic equation. We've seen it when we were doing factoring before. We're actually going to take one where the variables a, b, and c are filled out. So we're going to say this is our expression. Y is equal to 2x squared plus 3x minus 1. Now we know our a, b, and c. Those aren't terribly important for what we're about to do right now. Another way I can find out if an expression is quadratic, for instance, if they've given me this expression, okay, one way to tell if it is a quadratic or linear is we look at the degree of the expression. That is the variable with the highest exponent. What is the variable of the highest exponent? 2. So if we are to the second degree, we are quadratic. Okay? If it's to the first degree, so let's say we have, I'll write it in red, y equals 3x minus 1. The degree is what here? 1. If it's to the first degree, it's what? Linear. Very good. Okay? And if it's neither first or second, it's neither linear or quadratic. Now, last thing I need you to do. If you're given an expression or an equation like this, and you're asked to plot the points, we can plot the points by creating a table. Okay? So I create an XY table. I'm not sure why I had to make it so big there. We're going to make an XY table. Here's our X values and our Y values. I need to plot these on a graph. So I'm going to start at, let's say, -3. If my X value is -3, that means I take the equation here, and for each of the X values, I plug -3 in to solve for Y. So our first example, Y is equal to 2. That's not a 2. Times -3 squared plus 3 times -3 minus 1. -3 squared is +9. -3 times +3 is -9. Sorry, the other one was +9. Minus 1. 2 times 9 is 18. Minus 9 minus 1 is 8. So when x is -3, y is 8. That is a coordinate right there. Okay? Let's try another example. -2. We plug it into the formula again. 2 times -2 squared plus 3 times -2 minus 1. -2 squared is 4. 3 times -2 is -6 minus 1. 2 times 4 is 8 minus 6 minus 1 is 1. Here's another coordinate. So, if I was to start plotting this on a graph, here's our graph. -3, -2, -1, 0, 1, 2, 3. Let's say we got to go up to 8. 2, 4, 6, 8. At -3, we discovered we were at 8. So here's our first coordinate, -3 and 8. Our second coordinate we found were -2 and 1. -2 and 1. We continue this pattern to find out the rest. Oh, I should have known off the top of my head. 0 is going to be at -1. I'm just going to tell you that when you go to plug it in. So we plug in the next value. We're at 0, we're at negative 1. Sorry, that should be here. That's negative 2. That's negative 2, negative 4. Oh, I forgot to do the number negative 1. If we do negative 1 and plug it in quickly, we're going to get 2 minus 3 minus 1. Is that going to be negative 2? We better figure it out, just so we don't show you guys wrong. Same equation, y equals negative 2. We're plugging negative 1 in. Minus 1. We get negative 2 times 1 minus 3 minus 1 gives us negative 2 minus 3 minus 1. Does that give us negative 6? Is that right? I guess so. Oh, sorry, shouldn't have been negative 2, should have been positive 2. That's better. So now it's negative 2. So sorry, at negative 1, y is negative 2. So negative 1, we're at negative 2, which is here. When we're at 0, same idea, we plug it into our equation. Let's just quickly split that. Y equals 2 times 0 squared plus 3 times 0 minus 1. I can tell you right now that's going to give us negative 1. Okay? So at 0, we're at negative 1. So we're coming up again. That does not seem right. Anyways, what I want you guys to realize is we could continuously plug in x values and find coordinates for the y, and then we can plot them from there. So if you're given an equation, you can plug in x values, get the coordinates in a chart, is what we have here, and put them on a graph to eventually create whatever shape it is we're looking for.